Let's now look at a few more examples. So in this next example, we're asked to prove the reduction formula. The integral of cosine to the power n of x is equal to 1 over n times the n minus first power of cosine times sine plus n minus 1 over n times the integral of cosine of n minus 1. So this is called a reduction formula because the original integrand involved a cosine to the nth power, and this formula reduces it to the computation of an integral where the exponent is now n minus 2. So the exponent is dropped. And conceivably, this integral is now easier to work out than the previous one. How do we work out the integral of cos to the n minus 2? Well, we could apply the reduction formula again and reduce it to another integral of cos to the n minus 4. And then we could reduce that to cos n minus 6, and so on until we get that exponent down to something that's more manageable. Get it down to either 0 or 1. If it's 0, then that's the integral of a constant we won't work out. If it's the exponent is, we've reduced it down to a 1, then that's just the integral of a cosine function, which we can work out. So this is called the reduction formula because it takes a complicated integral and reduces it essentially by the exponent by 2 to make it what could be an easier integral to work out. So let's see how do we actually prove this reduction formula? Well, what we're going to do is we're going to apply by parts to it, and we're going to look through and see if we can pick out a piece of the original integrand that's able to be anti-differentiated easily, and the remaining piece will differentiate in hopes that the product of the resulting VDUs is able to be integrated, or at least reduced from the original integral. So here, I'm going to pick a piece that's something I can anti-differentiate. In this case, maybe the simplest thing would just be to take a single cosine. From the original integrand, those cos to the power of n, I'm going to take one of the cosines, put it as my dv, and then the other n minus 1 cosines we'll put over here with du. So I'm just going to make a little bit of space here. If dv is cosine of x dx, then the antiderivative is sine of x. And du in this case would be, well, it's n minus 1 times cos to the n minus 2 of x times the derivative. So here we're using the chain rule, times the derivative of the inside function. The derivative of cosine function is negative sine. So there's a sine x, and then we'll throw a negative out front. And there's our dx. So our original integral reduces now to sine of x cos to the n minus 1 of x, and minus the integral of the product of the two things, v and du. Since there's already a negative there, I'll make that a plus. So plus n minus 1 cos n minus 2 sine squared x dx. Just make that a little bit more clear. That's a square up there. Okay, so that's one application by parts. Okay, maybe it doesn't look like we made the original integral any simpler. What started out as a single power of a cosine now becomes a power of a cosine and a power of a sine. I forgot the x here. Okay, so what can we do? Well, we have an identity that allows us to rewrite the sine squared function as a thing involving cosine. So we're going to do that. So we've written sine squared as 1 minus cos squared. And now we can expand, and we get a cosine of n minus 2x minus n minus 1 cosine of n x dx. And so this can be split up into two integrals, one involving an integral of cos to the n minus 2, another one of cos to the n. And remember, all of this is equal to the integral of cos n of x. So again, we're in a situation where we've got the integral we're trying to solve tied up in an equation with some other functions and antiderivatives or integrals. So we can solve for this thing. I'm going to bring the integral to the other side. Right now it's over on the right as negative n minus 1, so I'll add n minus 1 times the integral to both sides. So this becomes an n times the integral of cos and the x dx. And that's equal to all of this, which we can now divide by n, which is the reduction formula that we wanted to show. So we've just shown that we can convert an integral involving an nth power of a cosine to another integral involving a power of a cosine where the exponent is 2 less. And we're now going to look at a couple of examples where we use this reduction formula to compute some integral powers of cosine. So let's look at computing the integral of cos squared x dx. By the reduction formula, this can be written as 1 over n, and in this case is 2, cos to the n minus 1, so now that's just cosine of x, times sine of x, plus n minus 1 over n, so that's 1/2, the integral of cos to the 0 of x dx, because the exponent here should be n minus 2, but the original exponent was n. So just keep in mind that that's just equal to 1. So this becomes 1/2 cos x sine x plus 1/2, and then the integral of 1 is just x. And then we have our arbitrary constant of integration. Notice we could also, so that's our final answer, but using trig identities we can always rewrite expressions involving trig functions, usually in various other ways. In this case we can write this one as so. And here we used the trig identity that sine 2x is equal to 2 cos x sine x. And this is the answer that we saw before when we used, instead of using a trig identity to reduce the result, we used a trigonometric identity to alter the integrand in order to make it easy to integrate. In this example, we just presented another solution for finding the antiderivative of cos squared through this reduction formula that we just constructed. Now, where the reduction formula actually comes in quite handy is, as in the next example, where we're asked to compute the integral cos to the power 4 of x dx. So with this fourth power, we can use the reduction formula again. And in this case, n is 4 in the reduction formula, so this would be 1/4 cosine cubed x sine x plus 3/4 times the integral cos squared x dx. And we already know a result for this integral. We worked it out in the previous example. So this becomes cos cubed x sine x plus 3/4 times 1/2 cos x sine x plus 1/2 x plus c in this case, which we could rewrite as 1/4 cos cubed x sine x plus 3/8 cos x sine x plus 3/8 x plus c. Right, so there's a couple of examples of how to first prove a reduction formula. And again, a reduction formula is just one that takes the original integral you're interested in and tries to relate it to another integral that's reduced in some way. And in this case, the reduction happened in the exponent. And then we use the reduction formula to work out some antiderivatives of various powers of cosine. And we could keep going. We could work out the integral of the 6th power of the cosine function by reducing it to the 4th power, and we've already got the 4th power worked out here. Let's look at this final example where we're looking at the definite integral now of the arctan function of 1 over x from 1 to root 3. So looking at this, it's not clear what the antiderivative of arctan is. At least I don't know it off the top of my head. I do know what the derivative is, so maybe I'll give a shot at using the technique that we used to compute the antiderivative of the logarithm before. We didn't know the antiderivative of the logarithm. I knew its derivative. So I used by parts by first taking u to be the integrand, and then dv to essentially just be 1, or 1 dx. And the derivative here of the arctangent function, it's 1 over 1 plus 1 over x all squared times the derivative of the inside function. This is through the chain rule, which is negative 1 over x squared dx. And the antiderivative here would then be just x. Antiderivative of 1 is just x. So by parts, our integral from 1 to root 3 of arctan of 1 over x dx is equal to x arctan of 1 over x, so the product of u and v, minus the integral of the product of v du. And now there's an extra negative sign already in du, so I'll make that a plus out front. And the product of v and du is x over, and then this x squared in the bottom can be multiplied through the two terms in the denominator of the other factor to give us an x squared plus 1 dx. So we've reduced our integral involving the arctan to an integral of a rational function. We also have some limits of integration, 1 to root 3 in both cases. Now let's go to work on this integral. So here we can use substitution. If we substitute for the denominator, we see that the derivative is up to a constant, it's just the numerator. This now reduces to x arctan of 1 over x. And what's our integral? Let's switch our limits as well. When x is root 3, that means w is 4. And when x is 1, that means w is 2. Just plugging it into the expression for w. So our new limits are from 2 to 4 of 1/2, and then it's a 1 over w dw. And so this becomes an x arctan of 1 over x from 1 to root 3 plus 1/2 the antiderivative of 1 over w. What is it? Logarithm, natural logarithm of absolute value w. Don't forget the absolute values here, because that's the full antiderivative of 1 over w. So that goes from 2 to 4. And so plugging everything in, we get this as root 3 arctan of 1 over root 3, that's pi by 6, minus 1 times arctan of 1 is pi by 4, plus 1/2 ln of 4 minus ln of 2. And ln of 4 is just 2, so note ln of 4 is just 2 times ln of 2, because 4 is 2 squared, and logarithms can be rewritten when your argument is written as an exponential. The exponent just drops out front. So this is 2 natural log of 2 minus natural log of 2, which is just natural log of 2. So this becomes then root 3 times pi by 6 minus pi by 4 plus 1/2 ln of 2. So there's our result. Alright, that's it for this lecture. Thank you very much for watching.